In the last video, we took a look at this really important idea that there is now a distinction between how we set up surface integrals for functions and how we can set them up for non-functions. The short synopsis was that if we had a non-function, something like the sphere, we needed to create a parameterization every single time. If we had something like a function that passed, say, a vertical line test, a z equaling stuff with x and y, then it was possible to skip the parameterization and just use the formula in the box above. Again, we could use the parameterization, but we don't have to. So let's take a look at something like example number 4 and see if we can get a sense of how this might actually work. Fully set up, but don't evaluate, the surface integral for this guy, where theta is the portion of the surface z equals tangent of y, which exists over this triangular region. Okay, so there's a couple new things that are starting to show up on this problem that haven't showed up on previous problems. First off, I'll note that the integrand that I have here is unbelievably scary looking. Like it looks so complex. Does this make the problem harder? No, not at all. This doesn't change the difficulty of the question by any means whatsoever. Okay, so we can actually ignore that. We'll see that whether we choose to do a parameterization route or a non-parameterization route, the function that's on the inside here doesn't really affect the setup. What else is different here is that I've been given a formula, and I've actually been told where this region is that I'm looking at the formula above. So I'm not looking at the full formula of z equals the tangent of y. I'm only looking at a part of it that exists above this region. So this is actually very similar to how we dealt with double integrals back in the previous chapter. And so what I'm going to actually go ahead and do to start here is to just try to think about two important things. First off, what is the region that I'm going to be integrating over? And second, how do I actually want to think about approaching this problem? Let's start actually by just trying to identify the region that we're working with. Okay, so I'll go ahead and say that we note D has the following picture. And I'm going to get ready to define D. It's going to be some set of points down in the xy plane, but I'm not sure which ones yet. All right, if I was to draw a picture here of my region D, I can note that it's a triangle determined by the point 0, 0, 1, 0, and 0, 1. And so my region D is right here. It's this guy. Okay, so this is my region D. I want to figure out how I can describe it. One thing that I'll note is that this line right here is pretty easy to find a formula for. It should just be the equation of y equals 1 minus x. With this in mind, I'm going to go ahead and bound this region here pretty simply. I can see that y on this region is bounded between 0 and that slanted line, 1 minus x. And x can then freely range from 0 over to 1. Okay. All right, so now that I have this, I would have a sense of what region I'm looking at this surface over. Now let's go ahead and think about what approach I would like to take. Do I want to parameterize my function and convert over the region that I'm working with to exist in the UV plane? Or do I have a function and I can just immediately jump to using the formula that we saw above? Well, I look here and I say, well, wait a minute, this is just a formula, z equals stuff with x's and y's. I mean, there aren't any x's in there, but that's fine. The formula has x's and or y's in it. And so this here is a function. So I'll state down here that since z equals tangent of xy is a function, we will use the previously described approach. Okay, so I can take this approach because I have a function. This is going to tell me that my double integral over sigma of my, let me get it written out here, this 2 cosine of y times this z minus tangent of y plus a 1 ds is actually just going to be equal to doing a double integral over d of my function that is my integrand just being fully updated let me actually write it up here, but it'll be, I have to update my function in terms of my variables and then multiply by this radical at the end. So to start here, my region D, I already know how that's been defined. I'll put my y variable bounds first, my x variable bounds second, so I know that at the end I'm going to have dy dx. For my function, I'm going to update this function in terms of x's and y's and z variables. So let's see, I'm going to have 2 cosine y. Nothing there needs to change because y is one of the differentials that I have. And then I have z minus tangent of y plus 1. Well, wait a minute. I don't really need z here because I'm only setting up an integral with y's and x's. So, I could just replace what z is the same as. I'll put in that tangent of y. Perfect. And then the only other thing that I need to make space for at the back is I needed to have this big radical back here. Okay. Remember that need to get some space in there for my dx. Remember that my radical here was just going to be, there we go. It was just going to be the partial derivatives of my z formula. So I have to start with partial derivative with respect to x, and then my partial derivative with respect to y being squared plus a 1. So in this case, my partial derivative with respect to x for my z formula is 0. Partial derivative with respect to y should just be secant squared of y, and then I just get plus 1. So I can go ahead and actually just clean this up a tiny bit. Although technically I'm done with everything the question has already asked me to do. So I have this 2 cosine of y. Notice I guess here that my next set of parentheses simplifies down to a 1, and my square root just is secant squared of y plus 1. dy dx. Everything's been fully set up. Again, the nice part here is I was able to circumvent actually having to do anything at all with the parameterization because I recognized that I had a function. And this is really the big key takeaway here. If I'm working with a function, I can avoid doing parameterizations.